everyone. I want to begin by welcoming you all to the video course on engineering geology. My name is Debashish Roy. I teach in the Department of Civil Engineering of Indian Institute of Technology, Kharagpur. My contact address is on the screen there. I can also be contacted via email at this address. There is Debashish at civil.iitkgp.arnet.in. All right. This course actually is going to be comprised of about 40 sessions, 40 1-hour sessions, out of which there will be about 35 or 36 sessions of instructions in the classroom, and the rest 3 or 4 sessions will be laboratory based instructions. So we'll visit lab, we'll try to identify some rock samples or try to identify different features on a geologic map. Those things will be taken care of in the laboratory. Rest of it, or for that matter, most of the things are going to be taken care of in the classroom. In the first session of this video course, we are going to cover some introductory topics that are of general interest in order to give you a flavor about what to expect out of this course. So what we are going to try to learn in this first lesson, we are going to try to learn what are the general scope and approach used in engineering geology. Then what are the typical assignments that one might expect while working as an engineering geologist, who might have to be interacted with when you work as an engineering geologist, who are the end users of the knowledge of this field of knowledge. And then finally we are going to actually talk about a summary of the historical developments that has led to the current state of knowledge in this field. So to begin with, we want to understand what is actually engineering geology, what are the definitions, what are the essential aspects considered in engineering geology. Now, as the name suggests, the field of engineering geology is actually a subtopic or a sub branch of the field of geology. Now, geology essentially involves studying of different aspects of or different processes involving different parts of the earth. Now, in order to understand what we learn, what we cover generally in geology, we try to understand first of all what is the structure of the earth. Now, you all know that earth is essentially a spherical body. The diameter or the radius of the earth, it is actually a little bit oblate. So the polar radius is a little bit smaller. This is the polar radius, that is a little bit smaller than the radius or the diameter at the equator. So the polar radius actually, or polar diameter for that matter, is about 2 times 6,356 kilometers, and the diameter at the equator is about 2 times 6,378 kilometers. Now so there is a difference of about 22 kilometers when you consider the diameter at the pole or that across the equator. Now, geologists concern themselves with the processes that actually covers the entire earth actually. So this entire sphere actually that is shown on the screen is what is dealt with by geologists, and you can understand that this is not a homogeneous structure, and the sphere, the oblate spheroid, actually can be subdivided into several different shell like zones. For instance, there is a zone which has got a thickness of between 5 kilometer and about 100 kilometer at the surface of the sphere, that is called the lithosphere. Now, this one has got a thickness of about 5 kilometer underneath oceans, and the thickness can go up to about 100 kilometers underneath where there are major mountain chains, and underneath the continents the thickness of this lithosphere is only about 35 kilometers. Now, underneath the lithosphere there is another shell, thicker shell actually, that is called the mantle. So, the one we talked about earlier was the lithosphere or the crust, and underneath the crust there is mantle that goes up to about 2500 about 2500 to 3000 kilometers measured from the surface, and below the mantle is the other unit that is called the core. All these different parts of the sphere, of the spherical structure, are different in terms of their properties or in terms of their density or in terms of the chemistry. So, the processes that are there in the lithosphere are not essentially the same as those one encounters in the mantle or those that take place in the core. Now, you all know that the construction, human activity, or the construction, I mean all the human engineering projects, they are confined within the top few tens of meters or at the most top few hundreds of meters from the surface. So, these are the particular things that are considered by engineering geologists. Engineering geologists deal with all processes that affect human activity or human habitat or human environment. So, what we are going to be concerned with? We are going to be concerned with the processes that take place over the top at the most 100 meter from the surface of the earth. So, we look at shallow crustal processes in engineering geology, shallow crustal geologic processes in this subject. What are those shallow crustal geologic processes? They could be mass wasting, something to do with slope failure or landslides. Then there could be near shore processes like erosion of the erosion due to the action of sea waves or waves generated on the river bodies or other water bodies. There could be deposition due to these wave actions or fluvial processes, that is also taken care of by engineering geologists in the near shore area. Then marine erosion and deposition, another topic of interest of the subject, and then fluvial processes, deposition, erosion, flooding, these kind of processes also are studied in the subject of engineering geology. Now, we need to understand essentials of the approach taken or the problem solving approach normally adopted in engineering geology. Now, it needs to be highlighted that engineering geologists are essentially geologists. They are not engineers, but they are geologists. So, they concern themselves only with engineering aspects. Now, you all know that mechanistic aspects are normally handled by engineers, and here we are looking at geotechnical or geological engineers who are mainly concerned with the mechanistic aspects of these geological processes. Now, that does not say that engineering geologists should not have a good understanding of the mechanistic aspect that drives these shallow crustal geologic processes, because if they do not understand the mechanistic aspects, then they cannot interact effectively with the engineers, geotechnical or geological engineers, who are ultimately going to be responsible for the construction processes of different projects. Okay. Now, we look at typical assignments that one might encounter while working as an engineering geologist. First class of assignment that one needs to handle as an engineering geologist is in resource management. What do you mean by resource management? Resource management essentially means that utilization of natural resources without harming the environment. Now, what are the resources that we need to worry about? We need to worry about groundwater resources, mineral resources, and forestry resources, to name a few. For instance, we need to exploit, if we need to exploit the groundwater resource, then we need to be very judicious about the use of groundwater. If the groundwater use is too much compared to the local geology or local meteorology, then that could cause undue harm to the environment. We will look at an example problem in this regard later on in this lesson. Then we need to also look at how to exploit mineral resources without judiciously, of course, to the maximum benefit of the construction activities or for the human livelihood. Now, mineral resources, you all know that mining activities, they actually are concerned with the exploitation of mineral resources. We also should look at how to exploit other types of resources to extract construction material for a particular type of construction project. And finally, forestry resources also is a very major part that engineering geologists deal with. We need to, for instance, when we are harvesting timber, then if there is an over harvesting or clear cut operation, clear cutting of huge areas, huge swaths of forests, then that could lead to disastrous consequences, like that could lead to enormous amount of erosion, and that can have a chain reaction to all aspects of human habitat locally as well as on a regional scale. The second aspect, the second type of assignment that we are going to deal with as engineering geologists is natural hazard assessment and risk management, of course. What do we do in that? We actually try to quantify the hazard involved in a particular area because of geologic processes. To give you a few examples, engineering geologists sometimes have got the responsibility of dealing with the hazard arising as a result of terrain stability. Out of terrain stability, we can by terrain stability what we mean is that landslide, mudslide, rock slide, debris flow, all these events are actually lumped together in this subtopic. So engineering geologists need to identify the hazard of terrain stability related hazards, and they need to quantify those hazards. So for instance, if an engineering geologist finds that in a certain area there is an undue hazard of landslide, then land use planners, they may decide that a particular project or settlement cannot be located in that particular situation. Earthquake hazard is another topic of interest in this regard. What do we do in that? We try to find out what is the likelihood of an earthquake to occur in a certain area. Engineering geologists are mainly entrusted in this regard to find out if there is any seismogenic source in the vicinity of a particular type of development, whether there is any active fault or volcano that could cause that could actually pose earthquake hazard to a particular development in the vicinity of those features. There is the quantification of the hazard is normally done by seismologists, and that is we are going to deal with that a little bit in the later part of this course, but in general the details of those things are within the scope of other branches of engineering and science. So in regards to earthquake hazard identification, engineering geologists are entrusted mainly with trying to identify whether there is any earthquake source nearby. The other thing is, of course, as I mentioned just a little bit ago, that volcanism is another aspect that one needs engineering geologists look at. Whether by that what I mean is that whether there is a volcano that is active or dormant, which might actually become active during the lifetime of a project or the settlement that is going to be constructed nearby. So these things are done by engineering geologists. Then they also deal with submarine hazards like likelihood of seafloor movement, whether there is any likelihood of turbidity current or tsunami caused by seafloor instability or earthquake taking place very near the seafloor. So these are the assignments typically are entrusted to engineering geologists, which involves assessment of natural hazard and risk management. The other class of problems that engineering geologists deal with is assessment of geologic hazard and risk that arises because of human activity. So far we were talking about geologic risk or geologic hazard because of natural processes. Now because of human activity also we could actually complicate or worsen the likelihood of a geologic hazard. Now we will consider a few examples in this regard. This kind of problems may be posed because of any big construction project like construction of dam, construction of railways or construction of highways. We are going to take an example like by considering a dam project. We all know that rock masses are comprised of joint sets. Now, let us consider a dam to be constructed on top of a rock mass that has got a joint set identified to be aligned like that is shown on the sketch there. So, these are the joints in between relatively intact rock masses. Now, say we want to construct a dam, a gravity dam, which is going to resist the pressure due to water primarily by its self weight. So, this is the dam, and it is going to actually retain water of that much of height. This could be, depending on the dam height, the height of reservoir could be several hundred feet. Now, this type of alignment, this type of alignment is not really preferred by engineering geologists, because the pressure of water which is going to act in that direction, that has got a component which is going to cause, which might actually trigger instability in the rock joints in that which are aligned as shown in the sketch. So, this kind of movement might be triggered if a dam is constructed as shown on the sketch. Now, if the dam on the other hand was to be located such that the water was on the other side of the dam, like let us modify this sketch to show what I mean. So, we just modified the sketch, we kept the joint set intact, but here we are going to construct the dam in such a manner that the water is on the other side with respect to the orientation of the joint set. Now, in this case, the pressure due to water is going to be aligned in the other direction, and a force aligned like this is unlikely to trigger any instability along the joint sets oriented dipping in that manner. So, this is a preferred orientation of the dam. So, if an engineering geologist is entrusted with a site selection for a dam site, he or she is going to look at these aspects of rock characteristics. Of course, I mean, these are not the only aspects. You should realize that in this introductory topic we are just trying to get a flavor of what is going to be generally expected in this field in the subject of engineering geology. So, we are not covering all the different aspects that are going to be considered while selecting a dam site. We are going to do that thing later on when we take these subjects up in more detail in due course of time. Okay. So, secondly, let us consider a railway project. or for that matter a highway project. These things are called linear developments because they have got a long they are relatively long corresponding to the lateral extent of the right of way. Now let us consider a typical linear development. It could be railway, or it could be a highway, or it could be a pipeline for that matter. Now what are the considerations that come in selection of a route for a railway or a highway or a pipeline? Now what has been known for a long time is that clay subgrade situation poses a lot of problem in this kind of development, because clays tend to settle, or they tend to behave in a problematic manner. They tend to develop uneven deflections or deformations under load over the course of the project life. So what is normally done is that if there are clay pockets, they are generally avoided while deciding a route for a highway or a railway or any other type of linear development. What I mean by that is, say you want to go from point A, or you want to construct a highway from point A to point B. Now there is a clay pocket we are actually looking at a map area in this sketch. So what we are looking at a plan view. Now we, as I was mentioning, that we are trying to construct a highway from point A to point B, and in between point A and point B there is a clay pocket which is as shown on the sketch. Now the shortest route from point A to point B is going to cut across the clay pocket. Now as I was mentioning, that clay pockets are normally notorious in terms of posing maintenance problem over the course of the project life. So these things are normally avoided, and a route that might be selected may be like this. So this is a preferred route perhaps, whereas this was the shortest route. Again, there may be other considerations depending on the local terrain or topography that may come up in this regard, like maybe over in this portion of the alignment there is an excessive hazard of landslide. So again, the engineering geologist may actually recommend that the route of the linear development from A to B follow the outer periphery, just outside of the landslide hazard zone. So finally what we end up with a route which is perhaps going to be like this. This is not the shortest route, and how the route is going to be aligned is going to be decided in close consultation with the engineering geologist. Okay, so that kind of gives a general idea about what kind of assignments that you might expect while working as an engineering geologist. Now who are the end users of the expertise? End users, as was very clear from the discussion that we had so far, the end users include mining and forestry industry. They are very heavily reliant on the knowledge of engineering geology. Then regulators and developers, they are also heavily tapped into the expertise of engineering geology. Land use planners, linear facility developers, project engineers and designers, they are actually some of the beneficiaries of the knowledge of engineering geology. Okay. Now, we are at a stage when we can take up a couple of example problems that you might actually have to deal with as if you decide to take a career of engineering geologist. One of those concerns mass wasting. What do you mean by mass wasting? Mass wasting includes landslide, mudslide, or any other kind of slope failure like rock slide or debris flow, rock avalanche, any of those type of problems that is dealt with, classified as mass wasting. Now, mass wasting can be triggered by natural cause like heavy rainfall or earthquake, or it can be caused because of human activity like road construction or deforestation. What do I mean by that is, for example, if there is a hill slope which looks like that, which is originally stable, we are looking at a section here, and then we decide to steepen the hill slope so as to accommodate a roadway and this type of steepening of the hill slope may actually trigger landslide like this manner. So over steepening of slope because of any construction activity may actually make an area susceptible to landslide or slope failure. Similarly, if the hillside is afforested and we actually indiscriminately cut down the trees, that is also going to increase the chances of slope instability. Now, in order to illustrate what we mean, we actually consider a configuration of slope which is shown on the sketch there, and what I actually want geometry before the slope failure and the alignment of the trees and other things. So you just have a close look at the sketch that is shown on the right hand side of the slide there. So all the trees are upright and we do not have any indication of slope failure as yet. Now we move on to the next slide, in which we are going to see an animation of slope failure. I want you to see what happens to the orientation or to the uprightness of the individual trees, and you just take a close look about what are the other features that you can identify during the mass wasting process. Okay. Now what we see here, first of all, we saw that there was a crack that developed near the top of the slope. That was kind of a precursor to the problem of impending slope failure. So there was a development of crack near the top of the slope, and then what we saw is that a scarp that actually opened up again near the top of the slope, from where the sliding mass actually came tumbling down. So this is called the main scarp. And then there were other scarps that developed in the process of slope failure. we saw that this tree, which was originally upright, got tilted in the process of slope failure. We also saw that there was a bulge that appeared near the bottom of the slope, which is also called the toe of the slope. So this thing is called, we could call it toe bulge. So what is the precursor then of a slope failure? If you see that a crack is starting to appear near the top of a relatively steep slope, then that is considered sometimes as a precursor to an impending slope failure. What is actually an indication of an ongoing slope instability? All the other features that I actually marked here, like presence of a main scarp, which is on one side is a relatively flat slope, and on the other side the slope is relatively steep and more steep compared to any other portion of the slope. That is an indicator of ongoing or a ongoing slope failure, or a process that has been there that developed over a recent past. Now if this feature is very old, then what is going to happen, of course, because of erosion, the steep portion of the main scarp is going to flatten out, and the area is going to be again vegetated. So these things, this feature is going to vanish, is going to be erased as the time progresses. If you see toe bulge near the bottom of the slope, not one bulge actually, there could be hummocky topography comprised of several different bulges. That is also indicative of an ongoing or an earlier slope instability. So these are the things that geologists are going to look for to find out whether a slope is going to be stable or it has got some likelihood of getting mobilized there is a possibility of slope instability. Okay, now this is what we discussed just a little bit back. The precursors to slope instability is that if there is appearance of crack, or if there is a seepage coming out from near the bottom of the slope, that is an indicator of impending slope instability. Then other indicators of ongoing or slope instability in the recent past includes uneven ground surface near the bottom of the slope. Then there are scarp like features along the slope face, or tilted tree or tilted telegraph pole, or any other type of man-made thing that got tilted, that was constructed originally in an upright geometry, which is now tilted. So these all things are considered as indicators of slope instability or mass wasting. Now the other problem, another example problem that we are going to consider here is ingress of salinity. What actually causes ingress of salinity? Ingress of salinity is caused in the coastal area because of heavy tapping of groundwater resources. If groundwater is tapped more, then the replenishment of groundwater because of rainfall or other types of precipitation, that causes a drawdown in the groundwater, and when the groundwater gets drawn down, then in the coastal area saline water gets into the it gets further inland, and that actually makes the groundwater wells and other things brackish. All the groundwater resources that can be tapped become brackish. So we are going to look at how this thing develops over the next couple of slides. So what we begin with? We begin with a geometry like that. Again we are looking at a section here where we have got a coastline. This is the coastline, and that is the sea level. So this water here, this one, this is actually saline water, and the water on the right hand side is fresh water. So what we consider here, we consider that a well, water well, irrigation well is installed at that location, and we will in the next slide we will try to see how the initial extent of salinity progresses to a location which is farther quite a ways on the inland. So you can see what happens actually, what is the outcome of this is that the water well is going to actually start tapping brackish water in this kind of situation, because the entire water from the sea coast to this far inland has become saline. So how does it happen? This actually shows an animation which will let you see how saline water, which was initially at that location there, it progresses inland. Okay. Now water table has drawn down up to that level because of groundwater tapping. Now what happens actually, let's start it again. What happens actually, because of the drawdown, the slope of the top of the groundwater actually pulls the saline water further inland, and because of the fact that brackish water is heavier than fresh water, the water that gets on top of the fresh water, that actually pushes the fresh water out, and in that process the brackish water is going to make an advance up to the extent that is shown on this particular slide. Let us look at it again. Pay a careful attention to the sequence of events. So this was the original configuration. This is when the water was pushed on top of the originally fresh water, and now it is going to push everything down because of gravitational because of gravity, and finally we end up with brackish water up to that location. So initially, so this is the final extent, if you recall, extent of salinity, and as I mentioned earlier, this was the initial extent of salinity. Once again, the water that is being tapped by this water well is tapping into brackish water only. So whatever area this water well is going to start irrigating, that is going to be affected by salinity. Okay. So salinity ingress, what are the precursor? Precursor is that if you have got seasonal or temporary salinity showing up in irrigation water, that could be considered as a precursor of salinity ingress. Now, what are the fixes? The fixes are restricted groundwater use, of course, and facilitation of recharge. Now, how much groundwater one could safely tap in this kind of situation is often quantified by engineering geologists. Okay. In the final segment of this particular lesson, we are going to look at what are the historical developments that has led to the current state of understanding of the subject of engineering geology. Now, use of geologic resources and heavy construction actually dates back to several thousand years. One could, for example, give an example of mining and metallurgy, then religious or ritualistic facilities, ports, lighthouse and bridges construction, occasional knowledge of what works and what does not work was there for development of this particular heavy construction, but what was not there is a scientific understanding of why a certain thing works and why some other things do not work. So, what I want to highlight here is that there has been history which dates back several thousand years of heavy construction. I mean, extremely large civil engineering projects we can think about, very like, for example, pyramids of Egypt or the Taj Mahal. I mean, we can talk about several different heavy construction activities over the history of humankind, but most of the time these things relied on the knowledge, on rules of thumb that told the construction people whether something is going to work or something is not going to work. So, what I mean by that is that, say you have got a in several different occasions what was found that midways into the construction project one had to actually change the entire sequence or entire drawing, entire details of the project in order to make the project a success. This was primarily because of the fact that there was no knowledge, no scientific knowledge that from which one could predict, the engineers could predict whether a certain type of construction can be successfully implemented or not. Now, the other thing is the next bit of development took place after the 1800s, and this is when the transition from the approach based on the rule of thumb to the scientific approach began, and this was primarily pushed by the advancement, I mean by the advancement of the human civilization into areas which was not inhabited for the most part. So, what happened because of those spreading of human settlement is one of which was railway construction. I mean, railway construction was a prime instigator of the developments of that we get to see today about many different aspects of engineering geology. Then this happened actually, this thing actually happened between 1800s and 1900, early 1900s. Then early 1900s to mid 1900s, what happened actually was development of several analytical techniques and emergence of geotechnical and geological engineering in the process. Scientific knowledge, quantified, I mean calculative approaches to implement different scientific knowledges was actually starting to develop in this particular time frame. Now, after mid 1900s to present, the development is mainly in the area of instrumentation or different ways of investigative processes and remote sensing. These are the different types of different areas that actually started developing since mid 1900s, and in this process the sensitivity of humankind towards environmental protection also increased. So another branch of engineering that actually bifurcated from the general area, and that was geo-environmental engineering. So that was in a nutshell what was the historical development that led to the current state of practice in engineering geology. So now we try to summarize actually what was discussed in this lesson. So we actually presented an outline of the scope of engineering geology, what is the definition and what are the different types of problems that we consider in engineering geology, what is the approach, typical approach and end users that we encounter while working as an engineering geologist. Then we actually considered two problems of engineering geology to give you a flavor really about the general nature of problem that you might actually come up with, you might actually encounter during this course. And finally we considered a very brief point form summary of the historical development that actually led to the present state of practice in engineering geology. And to conclude, we actually leave you with a question set, and just note down these questions and try to solve these questions in your leisure. Some of the answers were very obvious from what was presented in this lesson, and some of which you have to think a little bit. You try to try to develop all the answers yourselves, and we are going to actually give you brief answers when we meet in the next class of this series of lectures. Thank you very much. Hello everyone, welcome to session 2 of the series of presentations on engineering geology. In this session we are going to talk about geologic structures, different types of landforms. We will try to recognize what are the various landforms that one might have to encounter while working as an engineering geologist. But before we get into the subject matter of today's presentation, I am going to take up the question set that I gave in the first of this series of lectures, and I am going to try to provide you the answers of the question set. The first question that we had in the last presentation was how engineering geology differs from geotechnical and geological engineering. Now the difference is essentially very tenuous. Only thing that I can think about is engineering geology is more inclined towards the geologic matters, while geotechnical and geological engineering deals primarily with the mechanical aspects of the different problems that are encountered in engineering geology. Then the second question that I asked was that what are the key factors that may trigger slope failure. Two of the major factors that causes slope failure are loss of strength, loss of shear strength of the material of which the slope is comprised. The major reasons for the loss of shear strength is basically we now try to understand, try to get an idea about different types of landforms that one might have to encounter in a fluvial set of questions that you should try in your leisure. And again, as we did in the last presentation, I am going to provide brief answers when we meet for the next lesson. You should try to explain the dip, strike, anticline, thrust fault and loess. You should explain whereas dunes are generally underlain by sand grain deposits. We could also have glacial deposits. Glacial deposits are listed here, and they are generally laid by ice. So, if they are directly laid underneath ice, they are called till. They could be glaciofluvial deposit, meltwater that originates from melting of glaciers like drumlin, esker or glacial outwash. Now, these things typically are elongated in the direction of the ice flow with their slope in the direction of ice flow in the up ice direction is generally gentler compared to generally steeper in comparison with the down ice direction. There could be glacial outwash deposit that are comprised of basically sand and gravel deposits, or there could be glaciolacustrine deposits that are fine grained deposits underneath glacial lakes. Okay, that in a nutshell summarizes different types of landforms. We looked at descriptions of different stratigraphic units. We looked at how to define them geometrically, and we tried to list a number of landforms that are encountered often in the branch of engineering geology. We finally end this session with a set of questions that you should try in your leisure, and again, as we did in the last presentation, I am going to provide brief answers when we meet for the next lesson. You should try to explain the dip, strike, anticline, thrust fault and loess. You should explain the slope on the windward and the lee side, whether the slope of a dune is likely to be steep on the windward or on the downwind direction, that is the lee side. And you should also try to answer whether a drumlin, what is going to be an orientation of a drumlin vis-a-vis ice movement. Okay, so you try to answer those questions, and I am going to provide the solutions when I meet you again for the third of this series of presentations. Thank you very much.